Hello, Math 1224. This is Dr. P with Lesson Launch 802. Archimedes got nothing on this. Now, if you've studied any math history, you may know that Archimedes, the ancient Greek mathematician, made some very important discoveries about volumes of figures like cones and pyramids and spheres. And he's well celebrated for those accomplishments. And in this video, we're going to show how we can use calculus to find the volume of a cone, which is going to be different from the technique that Archimedes used. But ours is a technique that generalizes to a lot of different figures, as we'll see in the next section. So let's take a look at this cone, which has, let's say, a height. One thing I've discovered is that it's very hard to make dotted lines using this stylus and this tablet. But let's say that the height of this is 6 centimeters. And let's say that the diameter of this cone, let's say that diameter is 4 centimeters. And the question we're going to ask in this video is, what is the volume of the cone? Now, I know that you are probably familiar with, or at least you've heard of, a formula for the volume of a cone. That formula is volume equals 1/3 times the height times pi times the radius squared. You've probably seen it written more like this, 1/3 pi r squared h. But I wrote it this way to highlight that there's a factor of 1/3 there, there's a height there, and then there's this pi r squared, which represents the area of the base. And then that simplifies to this. So we could actually use that formula here to foreshadow what the volume is going to be. That volume is going to be 1/3 pi times the radius squared. Now the radius is not 4 centimeters, that's the diameter, so the radius would be 2 centimeters, 2 squared, times h. H is 6. So I believe I'm going to come up with something like 8 pi, and then let's make sure that this has the proper units, 8 pi cubic centimeters. So if at the end of this video I don't get 8 pi cubic centimeters, then I guess I'm going to have to redo the whole thing. I don't know. I've never made that big of a mistake in a video before. So let's hope that we don't start now. Anyway, so what we're going to do is we're going to just step back from that calculation. I know that we know how to do this, and this may raise the question, well, why in the world do we need to find some other approach for finding the volume of a cone? But the answer is that this approach is going to generalize quite a bit. It's going to generalize to other types of figures. And it's actually useful to think about how it works in the case of a cone, because there's some nice geometry to do in the process of developing this. So anyway, I'm going to draw one more time the same cone. Actually, can I take the cone and just drag it down here? That'd be really cool. No, not without dragging this whole thing. Okay, I'll redraw. I still don't quite understand how explain everything separates text and other objects, because I always think when I start a new color, I'm going to get a totally separate object, but sometimes it likes to glue things together. Anyway, I'm digressing here. So here's the cone again. And let's see if I can get a good dotted line here. That's not bad. Okay. So again, dimensions of the cone are 4 centimeter diameter base, and then 6 centimeter height. Now our approach is going to be similar to what we did in the last video. We're going to try and find the volume this time, not an area but a volume, by cutting this figure into slices. And a typical slice is going to look like this. And it's going to have a little thickness. So it's going to be like a little cylinder. Now, that's one of several ways I could cut a cone. I could also cut a cone vertically like this. Chop, 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 chop. Can you see that? Chop, chop, chop. The reason I'm cutting this way, horizontally, is because I feel like that's going to produce slices whose volumes I can find pretty easily once I've figured out the right function. This slice here, it's a cylinder. I know what the volume of a cylinder is. So I think I'm going to start there. Anyway, to do this though, and this is always the thing with these problems, is we need to determine the direction in which we're going to slice, determine the direction of slicing. That is always a strategic choice. We usually make it based on what will make the calculus and the algebra as easy as possible. So we determine the direction of slicing, but then we need to set up some kind of a, roughly speaking, a coordinate system. Set up a coordinate system so that we can figure out how volumes of slices vary. Okay, so to illustrate, in this particular case, this slice is, I don't know, pretty big. That's awfully vague, but that's as good as I can do if I'm not quantifying. Okay, if I want to quantify, then I need to figure out how big this slice is compared to a slice up here, compared to the bottom slice down here, compared to slices near the top. I need to have some function which tells me, based on how high I am, what the volume of that slice is going to be. The volume of the slice will depend upon how high up from the base I am. So what we're going to do is we're going to define a variable which I'm going to call y, that's going to represent the height from the base of the cone, the center of the base, to the center of this slice. And then that y is going to run from 0, which is at the base itself, to the top of the cone, which is at 6 centimeters. So y is going to be a variable that runs from 0 to 6, and as y gets bigger, the volumes of these slices should get gradually smaller. All right, and then the next thing I'm going to have to do is write a function for the volume of a slice. And that's usually these two parts here. These are the really tricky part. Once I've done that, the integral is usually not so bad. I know in the last one we had one that was kind of a beast, but typically with these problems, we're able to do the integration without a whole ton of trouble. It's setting up the integral that is really a challenge. All right, so anyway, I'm going to put this in the corner here. Now, I want to make a few suggestions about ways of thinking about these problems. There's going to be quite a bit of geometry in this video, probably even more so than the last one. So a couple of geometry things that are useful and that are going to be tools for us throughout this section. One of them we did in the last video is the Pythagorean theorem. Now, I don't know if I'm going to use that here. I just wanted to record it as something that is useful for us to know when doing these problems. And then another useful thing is similarity, in particular looking for similar triangles. I'll just put similarity here, though. And then a third thing is looking at various cross-sections, not just cross-sections in the direction that we're slicing, but other cross-sections as well. I'm going to draw a vertical cross-section of this picture through the very center. The reason I want to do that is that for me anyway, I don't know about for you, but for me, thinking about a two-dimensional figure often is much more productive than thinking about a three-dimensional figure. Because with a two-dimensional figure, I can redraw that slice from the top diagram. I can redraw it like this. So that's what it would look like in this vertical cross-section here. And try and think about, well, if that's at height y from the bottom of the figure, then what is the width, or let's say the radius, of this slice? That's what I'm curious about. So anyway, so the question is, what is the radius of the slice at height y? Because if I can find the radius, then I think I can also get the volume. And the volumes are what I need to add up. All right, so let's actually blow this up a bit so I can work with it a little bit more cleanly here. All right, so what I know so far is that I've got a slice. It's horizontal. It is y units up from the base of this figure. And I guess that's about all I know right now. I'm trying to figure out what this, let me put that in a different color. I want to find out what this distance is here. Okay, well, what do I know? I know that the cone itself has a height of 6 centimeters. I'm just going to abbreviate by 6 for now. And I also know that the radius of the base of the cone is 2. So that actually tells me quite a bit. That tells me that this triangle here, it's a right triangle. And it's a right triangle in which the height, this 6 here, this height, is 3 times as long as the base. Now that's going to be true of any right triangle that I embed in this figure, including this one here. You see this one that I'm tracing out, the one that includes that slice that I was thinking about? That's also going to be a right triangle where the height is 3 times as long as the base, and that's by similarity. Algebraically, we can write that as 2 over 6, that's this base over this height. That's going to need to be equal to this radius, which I'm going to call r for now. Notice that's variable. It's not the radius of the cone itself. It's the radius of this slice over, and now I'm in a little bit of a poke here. How do I write the height of this triangle here? Now think about that for a second. I know the entire height of the cone is 6 centimeters. I know that the height from here to here, by our definition, was y centimeters. So I think that that makes that other height, the height of that triangle, 6 minus y. So I believe that's going to make the radius, I'm just going to solve that proportion by cross multiplying. 6 times r is going to equal 2 times 6 minus y. So that's going to give me 6r equals 12 minus 2y. And therefore r is, I think if I divide by 6, I get 2 minus 1/3 y. Now remember, I don't want a big old integral in terms of r. This whole thing I'm setting up in terms of y here. So I would like to have r in terms of y, and I think now I have it. That's 2 minus 1/3 y. And then once I know the radius, I can say the volume of that slice. Okay, now I just want to remind you at this point, this was just a 2-dimensional cartoon of a 3-dimensional picture. That picture was up here. And that slice, that's a cylinder, and I've now found the radius. It's 2 minus 1/3 y. So the volume of the slice is going to be, let's see, that's going to be, what is the volume of a cylinder anyway? Now that I think about it, I'm not, you know what, I think I remember it. It's pi r squared times the height. Well, that's pi, oh my gosh, is this going to fit? Pi times 2 minus 1/3, oh, just barely, y squared. And then, what's the height? Well, what's the height of that cylinder? You'll notice it's a very thin cylinder, and we cut it off by choosing some slicing thickness here. That's delta y. So anyway, that's the volume of that slice there. The slice shown in red in both of those pictures is pi times 2 minus 1/3 y squared times delta y. All right? Now, that's the volume of one slice. If I want to find the volume of the entire figure, then I need to take the integral. Let's change colors here. I'm going to take the integral from y equals 0 to y equals, what is its max value? I believe it's 6 of pi 2 minus 1/3 y squared. And then that delta y, as we let that go to 0, that becomes a dy. Okay, now this looks kind of gross, but you'll notice it's just a polynomial function. We're not going to have nearly as much trouble with this as we did with the last one, I think. This is going to be the integral from 0 to 6 of, let's see, I probably should have just gone ahead and taken that pi out, so I think I'll just do that now. Just to keep things as neat as possible inside. Integral 0 to 6 of, let's see, that's 4 minus, and then let's see, 2 times, let me show you what I'm doing. 2 times 2 times 1/3 y, negative 1/3 y. That's, I believe that's 4/3 y, and then plus, and then 1/3 y squared, that's 1/9 y squared dy. And I think we're ready to go on and take the antiderivative now. The antiderivative is 4y minus 2/3 y squared plus, oh boy, I believe that's going to be 1/27 y cubed and that's going to run from 0 to 6. All right, now remember, we're hoping to get, just taking stock here, I'm hoping that we will get, where was it? There it was. I'm hoping that we get 8 pi centimeters cubed. So now is the moment of truth. Will we get 8 pi centimeters cubed? All right, well, that's going to be pi. And then the lovely thing about this is I know that when I substitute y equals 0, each of these terms vanishes. So I really just need to worry about what each of these is when y is 6. So I get 4 times 6 minus 2/3 times 36 plus, oh boy, mental math test, 1/27 times 6 cubed. I believe that's 216, which is going to raise another interesting question here in just a minute, which is what is 1/27 of that? That's pi times 24 minus 2/3 of 36, also 24. Oh, that's convenient. And then 1/27 of 216, feel free to run it through a calculator, but I happen to know that actually is 8. So this comes out to 8 pi, just as advertised. So this calculation does agree with what we got earlier, but just by using the classic formula for the volume of a cube, or not cube, cone. That 8 pi cubic centimeters up there. Let's make sure and write the centimeters cubed here as well, because this is something that we put in actual real-world units. We should put the answer in real-world units. Okay, anyway, you might wonder, what was the point of all this? We had a formula, right? We had a formula for the volume of a cone. Well, one thing that's kind of cool about this, I don't know if you'll agree it's cool. I think it's very cool. When I was in grade school, I always wondered where the formula, that formula that I talked about earlier, V equals 1/3 pi r squared h, where does that come from? And in fact, why is it in general that if you have a cone on a base, even if it's a very irregular shaped base, if I build a cone on it, there we go. It's kind of gross looking, but you get the idea, I think. If I build a cone on that and create a three-dimensional solid, the volume is always 1/3 times the height times the area of the base. That's where that pi r squared came from. You might wonder, why in the world is it 1/3? Where does the 1/3 come from? And you can actually demonstrate where that comes from using calculus. It's not the only way that's ever been done, but it is a way that you can do it. And I'm hoping that we'll have time to talk about that in class, but I'm not sure. Main thing is I want to make sure you have a chance to practice doing all of the geometry involved in problems like these. And that's why I wanted to make this little list here. There are 3 things, 3 geometry techniques, knowledge, I don't know what you want to call them, but 3 things that you're going to be accountable for here. One is Pythagorean theorem. See if you can build a right triangle and use the Pythagorean theorem. I could have done that here, by the way, but it wouldn't have given me anything I wanted. I wasn't really interested at any time in the length of this lateral slope here. I was interested in heights and bases, which is why I needed to use similarity. That's the second thing. And then the third thing is, if a 3-dimensional figure is too much, look at a 2-dimensional cross-section that captures most of the geometry of the figure you're playing with. So anyway, that's it for now. I hope this was informative, and I will not see you in class. Dr. Dueñas will see you in class. I think you'll have a challenging problem set there, which I've created. I think it's going to be a challenge, but he will be there to help you, and I hope that you learn quite a bit in class. And I'll see you next week. No more videos for Wednesday because it's an exam day. My goodness. Well, I'll miss you all, but I'll try and have fun at the state capitol. You have fun taking your test. Okay, I'll stop being a pain now. See you next week.